going to see the third problem. Here in this problem, there is a pipeline which is attached with the nozzle. So pipe cross section we are considering as 1 and the nozzle part is considering as a 2 section. Nozzle means all of you know that to the main pipe a cross section which going on decreasing. This part is called as a nozzle part. Okay, so in this problem the diameter of pipe is given as 400 millimeter. After converting it becomes 0.4 meter. Then the area will got here 0.001256 meters square. Then the nozzle having the diameter given 20 millimeter. Then after converting this 0.02 meter and the area of this nozzle becomes 0.000314 meters square. As well as in this problem, discharge is also given. The water is flowing through this pipe having the discharge of 1.2 meter cube per minutes. So we have to convert this meter cube per minutes into meter cube per second. So that's why I'm going to divide it by 60. Then I got the discharge here 0.02 meter cube per second. After calculating the discharge, the next step is to calculate find out the velocity at 1 that is the pipe cross section. So V1 is equal to Q upon A1. The value of Q is equal to 0.02 divided by area 0.001256, and here this V1 comes 15.92 meter per second. Then find out the velocity at nozzle. Nozzle nothing but it is the tapering reducing part. So V2 is equal to Q upon A2. Q is equal to 0.02 upon area is 0.000314, and here after calculating we'll get the value of 63.69 meter per second. Apply the Bernoulli's equation. So applying Bernoulli's equation at section 1 and 2. So P1 upon rho g plus V1 square upon 2g plus Z1 is equal to P2 upon rho g plus V2 square upon 2g plus Z2. Okay, so here Z1 is equal to Z2 because this pipe is at the same bottom line. Similarly, when the water is flowing through this pipe, it will come outside the pipe through the nozzle. So the P2 upon rho g becomes 0 because when the water will come out, the atmospheric pressure will be act. So the P upon rho P2 upon rho g becomes 0, atmospheric pressure acting on that. So now I am going to put the values for the remaining one. P1 upon rho g is equal to V2 square upon 2g minus V1 square upon 2g. Okay, now I am going to put the values. P1 upon rho g is equal to value of V2 square upon 2g minus V1 square upon 2g. The value of V2 is 63.69 square upon 2 into 9.81 minus V1 is equal to 15.92 square divided by 2 into 9.81. After calculating, here I got the value here 193.83 meter of water. This is a pressure head. So you have to convert into pressure. 193.83 into rho, that is 1000, into 9.81. This value is comes 190.1472 Newton per meter square. So here we got the value of P1. Now find out the force exerting along the x direction, because here along the y direction there is no component. So applying the impulse momentum equation, that is net force acting along the x direction is equal to rate of change of momentum. So now take the net force acting along the x direction. This is P1A1. Then the force acting along the x direction we are considering along this, that is Fx. So the reaction will comes minus Fx. Then the second force is minus P2A2 minus Fx is equal to mass flow rate, that is rho q, and change in momentum. Change in momentum, that is final velocity minus initial velocity. So when I am going to rearrange the term, Fx is equal to, here I got rho q V1 minus V2 plus P1A1 minus P2A2. Now put the values of these terms. Rho is 1000, Q is equal to 0.02, V1 is equal to 15.92 minus V2 is equal to 63.69 plus P1 is equal to 1901472 into A1 is equal to 0.001256 minus P2. Here P2, as we know that it is atmospheric pressure, so this term becomes 0. So here I got the value force exerted along the x direction, that is minus 1472.09 Newton, and this minus sign indicates that the resultant force is acting from right to left. Okay.